going to model with exponential growth and decay. And the first problem here, it says the bacteria count in the heated swimming pool is 1,500 bacteria per cubic centimeter on Monday morning at 8 a.m. And the count doubles each day thereafter. And our first question says, what bacteria count can you expect on Wednesday at 8 a.m.? Well, let's make our table before we go ahead and answer that question. And so at Monday at 8 a.m., what happens is we're starting with 1,500 bacteria. And what the problem again says is that the bacteria count doubles every day thereafter. So Tuesday morning at 8 a.m., how much bacteria do we have? Tiffany? 3,000 cubic centimeters. And then on Wednesday, what's going to happen is our bacteria is going to double again. And we get 6,000. And on Thursday, we're going to double again. And we get 12,000 cubic centimeters of bacteria. And then on Friday, doubles again. 24,000. And finally on Saturday, we double one more time. And we don't stop here, but that's all that we've got in our chart here. We've got 48,000 cubic centimeters of bacteria. So what bacteria count can we expect on Wednesday now that we have our table filled in? Tiffany? Monday, Tuesday, Wednesday.
Oh, oops.
That's all right. 6,000 cubic centimeters. So, suppose we want to know the expected bacteria count at 2 p.m. on Thursday, 3.25 days after the initial count. Can we use our table to help us estimate? We're not going to get it exactly. And we can put it in words, but how can we do that? Here?
You just take what it is at 3 days.
At 3 days.
And then you find out a quarter of that and add those together.
He said, take the bacteria at 3 days. Looking at our chart, this is 12,000. And then he says, take a quarter of that. Well, a quarter of that is the 0.25. That's quarter of that. So if we pull out our calculators and we type that into our calculator here, we get 12,000 plus 0.25 times 12,000. And we end up with 15,000 cubic centimeters of bacteria. And I think we'll leave it in mathematical terms rather than in words, in terms of explaining. But if we want to get the answer to this question more accurately, it would be helpful if we could write a function for the bacteria count in terms of the number of days since Monday at 8 a.m. And to do this, it's helpful to look for a pattern. So if you think back to what we've been studying this week, what were we doing in our table every single time to get from one to the next? We were always doubling. We're always doubling. So if we look back at the question here, if you began with a count of 1,500 bacteria, how do you get the number of bacteria after 1 day? Well, we're going to double that value. And then if we want the bacteria after 2 days, we had to double that value. Double our previous day's value. So we had to double, I'm going to write that, the previous day's value. And in fact, that's what we did. After 2 days, we doubled it. After 3 days, we doubled that. After 4 days, we doubled that. So what you can see from the answer of those 2 questions here is that the pattern in this, one of the patterns at least, is that we're doubling. So a pattern is to double. And then what it says is, it says, as the number of days increases, what stays the same in the expressions for the number of bacteria? Well, what stays the same is the doubling. And there's one more thing. Do you know what the other thing is that stays the same? Eric? Units that we measured in. Hayden? Well, because maybe. It's actually the initial value. And I'm going to put the initial 1,500 cubic centimeters. That's not going to change. We started with that amount of bacteria in the pool, and then we're using it to double. But we're not going to change that. It's not going to change on day 3. We don't go back and say, oh, we accidentally had more. And then what is changing, and Hayden, that's actually what is changing. The changing is the number of days. That's what's changing. So once we identify those facts, we can come up with a function to write out what we've been working with here for our bacteria. It says, use the pattern from above to write a function, P. This stands for population in terms of time. That represents the number of bacteria per cubic centimeters after T days. And we can check a few values for T to ensure the function. But what we're going to say is, well, we're always doubling. So it's going to be 2 to the T. And we've seen a lot of those functions this week, where we've been dealing with our base of 2. But now what's going to happen is, we're starting with the value of 1,500. And that 1,500 is going to double. So for instance, if we say T is 2, it says check a few values. Let's just check one. If we say T is 2, we can pull out our calculators and we can type in 1,500 parentheses 2 to the 2. And does that match what's in our table above? And if we go back, sure enough, we match. And we could check more. And in fact, we'll look here in a couple minutes. We're spending a lot of time on this problem today. So now we estimated So now we're going to use this function to determine the number of bacteria present after 3.25 days. We estimated a little bit earlier here. Now we're going to try to figure that out. And what that means for us is we're going to put in the value of 3.25 back into our function wherever we see t. So this is going to be 1500 times 2 to the 3.25. And again, we can take out our calculators and we can type in that value. You want a calculator to do this. So it's 1500 times 2 to the 3.25. And now we're going to get an exact value. We had to estimate it before, but roughly what it looks like we end up with is 14,270. And then we've got a part of a bacteria, so 14,270 and a teeny bit more. There's our number there. Once we have the function, we can figure that out. So when we did our estimate, did we underestimate the bacteria or overestimate the bacteria? We got 15,000, so we overestimated. But it was still a reasonable estimate. So as we flip our page here, what we're going to do now is we're going to type this calculator, or type this function back into our calculator. And that's going to go back into the y equals section of the calculator. And I just want to take a look at this function here when we go back and we type this in. So it's 1500 at the y equals, parentheses, 2, close the parentheses, caret, and then we're going to type in our variable, which is t in the formula. But on our calculator, remember, window, then mode, then x comma t comma theta comma n. We're going to use that button there right beside the alpha button. It's going to be x. And if we go to our table, like we were practicing yesterday, second in table, when we go back and look at this, look at what we get. 0, 1500, 1, 3000, 2, 6000, 3, 12,000, 4, 24,000, 5, 48,000, 6, 96,000. We get all of those values. In fact, we didn't even do the 6 on our table. But there's our values that went in the table. But what this one says is we want to look at the picture here, and it says adjust your window so that you can see the shape of the graph and sketch the graph below using a few key points, especially the y-intercept. So to go to the window function, it's here. And I have some change. I do want to change mine just a little bit from last period here. In fact, I'll just do, I can't do that. So anyway, I put 0 in for the X-Men. And then I put 10 in for the max, and I left the X scale as 1. Down here, though, on the Y min, I think I want to change it to -10. And then I put it to 1,000,000, but I think I'm going to change it to 100,000. And I'm going to leave my scale in terms of 100. And see if I have a little bit better picture. So when we draw the graph, maybe a little bit better. Because, so if we come back over here and fill in what we just filled in, we had 0, 10, 1. Then I did 0, nope, I did -5. And 100,000. And then 100 for the scale. And how did I get that? I played around with it a little bit. And I don't know if it showed up a little bit different on my calculator when I was sitting at a desk. Because it's hard to see, but our picture here Looks roughly like that. And what it says is, it says label a few key points. Well, if you remember from the table that we just looked at a minute ago, our first value was 0, 1500, and that's our y-intercept. And then we could come up with another value here on our table, just by looking at the table. If we go to second and table, well, the next point on here is 1, 3000. So we could do something like 1, 3000 as another point there on a graph. And I just got those numbers from the table. Now it says using the graph. For TI-84 users, we type in second, calculate in number 1. For Inspire users, I bet you have to go to menu, and I do need to look. I got to get batteries for my calculator to do that, but I can help at some point here with the Inspires. But what we want to know is find the y-coordinate when x is 3.25. And we already know what the value is. We found it algebraically just a minute ago. But how can we find it on our calculator? We go to second, and then calculate, which is this trace button. If you look above it, it says CALC, trace, and number 1 says value. What we're going to type in there is we're going to type in 3.25. When we type that in, look at what we ended up with. The same value that we came up with algebraically a few minutes ago. So it says find the y-coordinate when x is 3.25. Well, it's 14,270.485, which we just rounded a little bit on the front there in terms of the bacteria. And that should look familiar to you. But if nothing is done, and the bacteria continue to double, continue to double, how long will it take the count to reach 3 million bacteria? Well, let's write an equation for that. And what that says is we know that our answer is 3 million. Our function's not going to change. It's still, we start with 1500, and we're going to double each day. I'm going to write a T there instead of an X. We're going to double each day. So we're going to use our table on our calculator to figure out which 2 days will reach between 3 million. And when we go over here, second and graph, like we practiced yesterday, on this calculator screen up here, and it depends on the screen. Some of them do it and some of them don't. We've seen these numbers here from the 1500 to the 48,000, then we double, and we're doubling, and we're doubling, and we're doubling. So when we double the 768,000, what we ended up with here is 1.54 e to the 6th. That's in scientific notation. But if we double 768,000, what you might realize is that we're getting 1,540,000 or so bacteria. And as we scroll through our screen here, on day 11, we get 700,000, I think, 3,070,000 bacteria. Well, what we're looking for is between which 2 days will our count reach 3 million. I'm going to scroll down one more here. That didn't work. But what happens is 1.5 million, 3.07 million, it's going to be between days 10 and 11. And it depends on your calculator. 10 and 11. I should put day 10 and 11. We're not going to find the exact number. But day 10 doesn't have enough, day 11 has more. So somewhere in between there. And the thing to ponder here, something to think about, is can we solve the equation we wrote in problem 9 algebraically? Well, we don't know how to do it yet, but hopefully soon we're going to learn how to do that. So far, what we've been dealing with this week is we've been dealing with exponentials in this form, y equals b to the x. And in general, to write an exponential function that models a real-world scenario, we need two things. We need the initial value, which in the case of the problem that we've been working with for most of our time here, is going to be the 1500. That's going to be our a in this equation. And the rate at which the pattern grows or decreases, as the case may be, is the b. So we've been doubling in the problem that we've been working with. Always think of the pattern in terms of what you need to multiply by to get the next number in the list. So even though we won't get completely finished here with this last example, I do want to try to get through at least one and maybe two. We'll see. I might be ambitious here. But Maria made a half a gallon of fresh orange juice on Saturday evening for Sunday's breakfast. In the middle of the night, Liesel got terribly thirsty and she drank half the fresh orange juice. She didn't want anybody to know, so she filled the jug back up with water. And then Friedrich, I think, got up and he did the same thing. He was super thirsty. He drank half the jug of the orange juice. And he's like, oh, I drank so much. I better fix that so no one knows. And he filled it up with water again. And then it kept happening. Louisa did that. And then Kurt did that. And Brigitte did that. And Marta did that. And Gretel did that. Let's make our table here. And we started here, first of all, with 64 ounces of orange juice. So when Liesel got this, it says, write a function that represents the amount of fresh orange juice left in the picture. So after Liesel drank her orange juice, how much fresh orange juice is left in the picture? Jordan?
32.
32. 32 ounces. And then how much is left after Friedrich drank the orange juice? 16. And how much is left after Louisa? Tiffany? And then after Kurt? That's like 4. But you might be ahead of me, because now it's going to be 2. Then Marta? What's our pattern here? What are we doing? Jordan? Dividing by 2. We're halving these. So there's not very much orange juice left by the time Gretel gets to that. So if we want to write this function here, what's our initial value in this problem? What did we start with? 64. And what's our pattern? Well, we're dividing by 2. Or, in other words, we drank half of the orange juice. So when we write our function here in the format of f of x equals a b to the x, our function's going to be 64. There's our initial value. times 1/2 to the x. So then, here to look at this next part. Sunday morning, George wakes up early and is so thirsty that he wants to have some orange juice before everyone else wakes up. Well, using the function from above as well as the table to confirm your answer, determine the amount of orange juice that will be left after George has his fill. Well, if we look here at our table, George is going to be number 8. So when we fill this in, this is going to be 64 times 1/2 to the 8. But is there any common sense there that you could have used to figure it out? Because the question says, determine the amount of orange juice that will be left after George has his fill. Tiffany?
I just say divide what was 0.5 and half into 0.25.
0.25 or 1/4 ounce left. You could have looked back at the table and divided by 2.